All right, let's go ahead and take a look at explore number 2 of understanding and describing motion. We'll start by uh, getting our template for taking notes ready here. Go ahead and write down the date that you're taking these notes. Okay. And actually, let me just take this up to 100% here. Where am I here? There we go. That should work there. Let's see here. Let's just kind of recalibrate things here. I'm sorry about that. All right, so you're going to write the date, and we're going to write our essential question here. How can physicists use Newton's laws? How can physicists use Newton's laws of motion and universal gravitation to predict objects' motions? Question mark. Okay, that ought to do it for us. And let's have you guys hit pause and write down what you know. Okay, take a moment, if you will, and just write down a sentence or two. Remember, this is all designed to help you push yourself to actively engage with the content and learn this information. Okay, if you've already finished up, we'll go ahead and jump into it, okay? I can see that we're going to talk about forces on objects. I'm taking a look at kind of these paragraph titles here. Forces on objects, Newton's laws of universal gravitation. I can see I've got some vocabulary words in here. Got some videos to help me in my understanding. I got 3 sections here. Newton's. This is a sample problem. Okay. And then we've got a section called validity and usefulness of Newton's laws. So there's our 3rd section, perhaps. And then we've got some homework problems, and that's it. Okay, so that kind of helps us in laying out our notes there. Okay, so Roman number 1, forces on objects. As you remember in class, we've been referencing or talking about frames of reference. Okay, frames of reference. And, if you could be in a car driving towards another car, both of your cars are approaching each other, and from your perspective, the car would be moving very, very fast, but that's because both you and the car are approaching each other. If, on the other hand, one car was stopped while you were driving towards it at the same speed, it may not appear as fast. And again, that's because you have different frames of reference. Another example could be if I was in a car driving 80 miles an hour and um, a passenger, let's say, I wasn't doing anything. I was just sitting there in the car. Well, to somebody else in the car, it would look like I'm not doing anything. But to somebody on the side of the freeway, they would see me drive by 80 miles an hour and they would say I was moving very fast. So again, you have different frames of reference. Okay. Uh, Physicists can analyze and predict changes in objects' motion positions over time. That is their motion. Okay, so let's go ahead and just put this down first. What is motion? Um, Changes in an object's position over time. Okay. If we are curious enough and want a good working definition for frame of reference, we just have to click the vocabulary. Let's take this off of tablet mode for a second. And there we go, frame of reference. A detailed definition says an item against which the motion of an object can be measured. Okay, well, let's go ahead and just write that all down there. An item against which the motion of an object can be measured. Maybe I can just kind of reduce that size just a little bit. And we'll say number 2. Frame of reference is an item against which the motion of an object can be measured. Okay. And key context, this is always important. I encourage you to take a look at that as well. Okay. All right. Sir Isaac Newton, Newtonian physics. He's the one that really kind of explained the world as you and I see it, how objects move in this world. Newton's laws of universal gravitation. Okay, so let's go ahead and write this down here. This will be Roman numeral 2. Newton's law of universal gravitation. All right, that's what we just wrote right here. Newton's law of universal gravitation. Okay. And basically, this is an explanation, as you can see in your text. This is an explanation for the way gravity works. In Newton's law of universal gravitation, he showed that what? The force due to gravity. Okay. He showed that the force due to gravity, F of g, due to gravity, between two bodies is directly proportional to their mass, okay, is directly related to the mass of object 1 times the mass of object 2. So if the object's mass for m1, that's object 1, or m2, object 2, increases, then the force of gravity between them is going to increase. And it is inversely, so we're going to write a fraction, inversely proportional to the square of the distance of between the bodies. Okay, so over the r squared. Okay, this would be the distance between both objects. And this would be squared. And this is the mass in kilograms of object 1 and 2. Okay, and you would multiply those. There is also a gravitational constant that you'd have to multiply all of that times as well. And we're going to get to that in just a minute. Okay, but that's basically what that paragraph says there. Okay. And they go ahead and kind of give you some examples here, which I encourage you to read. They clarify and make sure you understand that mass is the amount of material that makes up an object. So if I have the mass of my body, or let's just say the mass of a bowling ball on Earth, does not change if I bring my bowling ball to the moon. It still has the same. It's still the same size. Still has the same amount of material in it. It won't change if I go to Jupiter. It'll still be the same size bowling ball. But what will change will be its weight. And the weight is a function of the amount of gravity. And Mars has a different force of gravity than Earth, and Earth has a different force of gravity than Jupiter. Okay, so mass is the amount of material that makes up an object, and the an object's weight is the force that the mass exerts in a gravitational field. Scientists use kilograms for mass, and they use newtons when talking about weight. Okay, I guess we should probably write some of these things down here. Note, mass is the amount of material in an object. We measure that in kilograms. Measure in kilograms. Weight is that mass multiplied times the field of gravity. The is the force that mass exerts in a gravitational field. Okay, because if you're not in a gravitational field, you're not going to feel any force. Your bowling ball is just going to feel like it's floating, as if you're in outer space. Okay, and that weight is going to be measured in newtons. Measured in newtons. All right. Okay. So we've got some formulas we're probably going to be examining here, some videos that are essential that you watch, okay? Now, we are not fully studying Newton's laws of universal gravitation, okay? This is just an introduction. There is a chapter just on this, okay? But watch these and start becoming comfortable with how it feels, okay? So we have an example problem here. So example, Newton's second law of motion. Well, let's see. We are going to get to the sample problem. Newton's second law of motion says that any force exerted on an object will cause that object to accelerate. any two objects with mass will exert a gravitational force on each other. This force will then create an acceleration that can be used to describe the motion of the two objects. Before the motion can be described, the force of gravity between the two objects must be found. Okay, so take a look at that G. They do give us, finally, what G is. G is Newton's gravitational constant. It is this number right here. Okay, so let's come back up here and write a note to ourselves because this is important. What is G? G is Newton's gravitational constant, which equals 6.67 times 10 to the negative 11 newtons times meter squared all over kilogram squared. Okay. All right. And now let's go to an example problem here. Okay, clear my screen. And move this up just a bit here. And let's just expand this here. So the moon and Earth have masses, okay, of 735.1022. So they give us the M1. Okay, we'll say that's the mass of Earth. And, that was the moon. And Earth is going to be M2. This has a mass of 5.98 times 10 to the 24th. A bigger number, that makes sense. The distance between these bodies is about 300. So this is going to be our, what we call R, okay, or our distance. 3.84 times 10 to the 8th meters. Notice that that's in meters. To calculate the force of gravity between them, use Newton's law of universal gravitation. All right, so in this example problem, you just simply, I don't even have to really write out this problem. Let's just go ahead and take a look at the screen. Just expand upon this, okay? So here's our gravitational constant. Here was our M1. Here was our M2. And underneath was the distance, R. And you had to, of course, square that. And that's why they have a squared number. Put that into the calculator, and you get a force of gravity that is 1.99 times 10 to the 20th newtons. Okay. This is what they just call plug and chug. You just plug your numbers in. Okay. And we got all these numbers from up here. This was M1, this was M2, and we knew that this was the gravitational constant was right there, and this was the R right there. Okay, and that's how you would use that equation. Clear your screen, and let's move on here. The validity and usefulness of Newton's laws. Newton's laws are most useful only within inertial frames of reference. Okay, so for the example, let's just say refer to Earth Moon problem in Explore 2. Okay, because they did a nice thing there. Now, what we do want to say here is a little note. This is important. Newton's laws are most useful within inertial frames of reference. Okay, they can be carefully modified for use in non-inertial frames of reference. So you can use them in both contexts, but you have to really be careful with the non-inertial. Okay, when objects are very tiny, such as atoms and molecules, they do not follow Newton's laws of motions. Another set of physics laws, quantum mechanics, works better. works best for that scale, very tiny things. And when objects travel very fast, more than about 1/10 of the speed of light, Newton's laws do not work well either. The theory of relativity is better used for describing those things that move at that speed. Okay, so there are restrictions. Okay, there are restrictions to this. There are constraints to the laws. Okay, these are the constraints down there. Okay, all right, and continue to move through here. And then, of course, you have some problems down in here. Okay, all right, so that pretty much covers it right now. All right, we kind of did some notes. We explored these different things. You want to make sure that your distance, maybe we should just make a note here, distance between both objects squared, we would say in meters, right? In meters. That's important. If it's not in meters, you're going to have to convert your units. Okay. Same thing with mass. You want it to be in kilograms. And that's it. All right. Let's go ahead and have you just write yourself a summary sentence. Okay. So we're just going to say, or maybe we should say a summary paragraph. Okay. And that'll do it. All right. We'll talk to you soon. All right. Bye-bye.